This will be a quick video walkthrough of how the Deimos toolkit works and how the examples work. What you can see here is a scene, an example scene, with all these different data visualizations. These data visualizations are built using DXR, a modified version of DXR, in order to support new data visualizations, such as a choropleth map, stacked bar chart, and faceted charts, and so on and so forth. The idea with Deimos is that these data visualizations have morphs, or animated transitions, applied to them at runtime, provided that they match specific conditions. So for example, we have this three-dimensional scatter plot here, and if I take the left hand of the MRTK simulator, and if I pinch, you can see that this turns red. Now other visualizations in the scene are also turning red because they match the same conditions. This rule is specified using this JSON file that you can see here. In this, we have the name of the morph, there's different states that exist within that morph, the signals, which are data sources used to control that morph, and the transitions, which connect multiple states together in order to create the animated transition itself. And so as you can see here, there's two states, an unhighlighted state and a highlighted state. And essentially what the system does is that at runtime, it checks to see whether or not any visualization matches the states. If it does, it's eligible for the transition that is defined down here. And that transition connects these two states such that it takes it from this unhighlighted state where it has no color encoding to a state where there is a color encoding. And this all can be updated at runtime. So for example, if I change this value to blue, what Deimos will now do after I refresh the morphs is that now if I do the same thing, it will change the blue. So these states are acting both as conditionals as well as ways to create the keyframes itself. And as another example, if I change this to cube, so it requires the mark to be a cube rather than a sphere. Now, this will not work on our visualizations, on these ones, because these are spheres and not cubes. So that's the general idea. And we can get into a lot more complex examples of these, of course. So, for example, this right here is the specification for tilt map, and there's a whole bunch of different examples in the example scene as well that I would highly encourage you to go through. But several examples of things that we can create is this geographic scatter plot that uses a linear slider, sort of reminiscent to a very typical conventional animated transition. We have a recreation of tilt map, which was originally created by Young et al., where if the visualization tilts, it transforms from a choropleth into a prism, into a bar chart, and vice versa, based on the tilt angle. So this is a very type of embodied transition that's only really possible in VR. These examples go further, like this one, for example, is a bar chart. If this bar chart collides with a surface, then it partitions out into facets. But if I take the same bar chart and I rotate it 90 degrees, then it stacks them up instead, as you can kind of see. The nice thing about this example is that these are two different visualization specifications under the hood, but the same morph is being applied to both of them because it's using this sort of dynamic matching to apply to multiple different types of transitions. So that's the general idea. This example scene you can find in the assets folder, assets, Deimos, examples, example morph scene, and you can have a play around with these different examples as you can see here. All of these morphs are loaded in this morph manager game object on the right, where you can see all the different specifications on the side with a check mark to say whether or not it's actually enabled and whether or not it's loaded. Hope that all makes sense. Feel free to explore this as you want. There is also as part of the supplementary material, there is also a document that goes through how to use Deimos, how to create a specification and write your own one, and explains some of the concepts as well in a slightly different manner than what was presented in the manuscript. Thank you for watching.